In October 2024, John Hopfield and Geoffrey Hinton received the Nobel Prize in Physics for foundational contributions that led to modern artificial intelligence. An unusual award, since neither is a physicist in the narrow sense. The prize honored a mathematical model that Hopfield formulated more than 40 years ago, and that was originally meant to do just one thing: remember images. Today, in a modernized form, that very model powers every large language model. Over the next few minutes, we trace the line that runs from the iron magnet of the 1920s to today's chatbot. Picture a hilly landscape with valleys of varying depth. Drop a ball into it, and it rolls downhill and comes to rest in a valley. A Hopfield network is barely more than that. The landscape becomes an energy function. The ball becomes a state of the network, and the rolling becomes a rule that changes that state step by step so that the energy decreases. Place the valleys exactly where stored patterns lie, and the rolling becomes recognition. A noisy image rolls into the nearest valley, and that valley is the stored original. Recognition as gravity. For the valleys to sit in the right places, the model uses an idea from Donald Hebb from 1949. Neurons that are active together strengthen their connection. From the stored patterns, a weight matrix is built. The update rule is strikingly simple. For each neuron, take the weighted sum of all the others and set its value to the sign of that sum. What matters is a guarantee that Hopfield proved. Every single step lowers the energy. Since the energy cannot fall forever, the network must come to rest after finitely many steps. This property is called, after the mathematician Alexander Lyapunov, a Lyapunov function. And it is the reason convergence here is not luck, but a theorem. So much for the idealized picture. Turn the model loose on real data, 10 handwritten digits, each stored on its own and recalled from a noisy version, and it breaks. Instead of 10 distinct memories, only one emerges. Every query rolls into the same valley, a state that is none of the digits anymore. The reason can be read off the spectrum of the matrix. A single eigenvalue dominates all the others by roughly tenfold, and its direction is almost exactly the average digit of all the patterns. Hebb's rule provably works only when the patterns are roughly orthogonal and balanced on average. Handwriting satisfies neither. The failure is therefore not a bug, but expected behavior outside the model's domain of validity. The repair is a single change in the construction. Between the two factors of the matrix, we insert the inverse of the Gram matrix of the patterns. This factor describes how strongly the stored patterns overlap, and removes exactly that overlap. From this construction follows a guarantee. Every stored pattern is mapped exactly onto itself, no matter how strongly the patterns are correlated. Anyone who knows the eigenvalues post on this blog will recognize the formula. It is ridge regression in the limit of no regularization. The same tool that smooths stock prices there places the valleys of memory in the right spots here. The pseudo-inverse, too, has a limit. Beyond a few hundred patterns, the basins of attraction shrink and recall collapses. The way out was found in 2020 by the group around Hubert Ramsauer. It gives up the fixed matrix and reevaluates, for each query, which stored patterns are relevant at all. The new rule has 3 steps. Measure the similarity to each pattern, turn those similarities into weights through a softmax, and average the patterns with those weights. The parameter beta controls how sharply the choice is made, from soft averaging to picking a single pattern. And here comes the real punchline. This exact operation was published by Vaswani and colleagues back in 2017 under a different name: attention, the mechanism at the heart of every transformer. Set the query equal to the query and the stored patterns equal to keys and values, and the two equations become identical. Not similar, not analogous. The same operation in 2 notations. Every language model carries out, for every word, a Hopfield iteration. One question remains: does the network also recognize? what it never stored. On handwriting, it does not. There, it stays a glorified nearest neighbor comparison. But that is not the fault of the learning rule. It is the fault of the data. When the world is made of a few building blocks, from which every pattern is composed, a three-stage behavior appears. With few patterns, the network memorizes individual cases. With more patterns, it discovers the shared building blocks. And with even more, unseen combinations of those blocks become stable memories too. Genuine generalization. This means only what has a sparse structure becomes recognizable. Language models generalize so well because language itself is made of such building blocks. If you want to follow this yourself, you'll find every one of these stages as an interactive demonstration on KI-Mathias.de. There you can turn up the noise on a digit and watch the network recognize it. Slide the attention sharpness parameter from soft averaging to picking a single pattern, and step through the transition from mere memorization to genuine generalization, phase by phase. The same operation shows up today in very different fields: in drug discovery, in the classification of antibody repertoires, on memory stored chips that solve NP-hard optimization problems in a single analog step, and in every transformer, usually without being called Hopfield. When the same structure is rediscovered independently in physics, in pattern recognition, in language processing, and in hardware, that is no coincidence. It is a sign that it was not invented but found. What Hopfield formulated in 1982 as a model of biological memory is today the architecture behind every language model. Anyone who knows the arc sees, in every chatbot reply, the iteration of a spin-glass model that originally could only recognize digits. The past is not closed. It is still running. The full post, with all the interactive demos to try for yourself, is on KI-Mathias.de.